Action. Expand. So we have the natural log. By the way, just to review, ln is log base what? E. It's log base E. It's the natural base. That's why we call it the natural log. So to expand it, we've got four factors. This desk is tiny. Let me scoot up one. All right, we got four factors, don't we? We got a 4, we got an x squared, we got a 3, and a y to the fourth. So we have properties that allow us to expand quotients and to expand factors. So your first step might be to do this: the natural log of 4x squared minus the natural log of 3y to the fourth. Would you do that first, maybe? Yeah, because I can subtract the one on the bottom. Now I can focus in the top. There's two factors, so that's the natural log of 4 plus the natural log of x squared. And then here I get minus the natural log of 3 minus the natural log of y to the fourth. They're both negative on the last two terms because both factors are in the denominator. Yes, yes? Okay, that's using property 2 and then property 1. And now we're going to use property 3, which says anytime you have an exponent, where can the exponents go? Out front. Do you have to make the sound effect? You can. You sure can. So this becomes the natural log of 4 plus the natural log of x times 2 minus the natural log of 3 and then minus 4 times the natural log of y. There you go. And that's Patrick. Yeah. Yeah. All right. So here's what I would like for you to be able to do. I would like for you to be able to go straight from there to there. That's your goal, without having to do those intermediate steps. All right. Basically, you're saying every factor gets an ln, right? Every one of the four factors gets its own ln. If it's in the numerator, it's a positive sign in front. If it's in the denominator, it's a negative sign in front. And where do all the exponents go? In front, okay? So you should be able to expand it in what I call one fell swoop. All right, questions on the warm-up. Are you warm? It's supposed to freeze like Sunday night. Did y'all know that or something like that? We're supposed to get Monday, yeah, it's supposed to be like cold, finally. Oh, for a brief moment, just to catch it on your tongue, and then it goes away. It's just kind of a pain in the butt if you're a husband or if you're a good son or daughter, because you got to bring all the plants in and then wrap the ones that can't come in, and then you got to wrap the pipes too, or put those covers on the pipes on the hose bibs. Yeah, so it's kind of a hassle. And then you got to put the chains on the tires, your snow chains on the tires. All right. Let's look at example 4. It says to prove property 2 and property 3 using the other properties of logs. This gives you an idea of how you can manipulate things abstractly without real numbers. Property 2 is this. Okay, remember property 2 said the natural log of A divided by B is the natural log of A minus the natural log of B. Now, we're going to do trig proofs later on in the year, and you're going to have a lot of fun doing them. When we do a proof, this is how we do it. We write out the equation like that, and we draw a line down the equal sign. Okay? And what your goal is you're trying to make the left side look like the right side. You can work on each side if you want, but you have to work on them independently. In other words, I can't just add like the natural log of b to both sides. I can't treat it like a conditional equation. I have to work with each expression independently, and once the left side looks like the right side, or the bottom line on the left side looks like the bottom line on the right side, you've completed the proof and you're done. Okay? Now, the goal here is to prove that it's true, but I can't use the property itself to prove that the property is true. But I can use the other properties. So here's what we're going to do. We're going to start on the left side here because it looks like it has more information. It has a quotient. So I'm going to say that this is the natural log of, I'm going to say it's the natural log of A times b to the negative first. Would you agree? Now the reason here, we don't have to write the reason, but if you ever had geometric proofs, you had to like put the reason like postulate 3.1 or theorem 4.5. Okay? Parallel postulate, whatever. Here the reason would just be rule of exponent, right? The reason would be rule of exponent. Dividing by b is the same as multiplying by b to the negative first. Once I've written it like that, I've written it as a product, so now I can use property 1 to say it's the natural log of A plus the natural log of b to the negative first. Yes, yes? That's using property 1, which is legal. I'm trying to prove property 2, so I can use property 1. Now what can I do with the negative 1 that's an exponent? I can bring it out front, and it becomes minus the natural log of b. That's using property 3, not property 2, which is legal. Now, aside from the color difference, does the left side look like the right side? Yeah, they're the same. So we usually put QED there, which is an acronym for Quid Erat Demonstratum. You might have seen that before. You may not. Quid erat demonstratum. Guess what language that is? It's Latin. Yeah, Latin is such a good language. Demonstratum. It has gravitas to it. Y'all know what that means in Latin? Something with demonstration, right? It's almost a cognate word. Demonstrate. The verb is erat, which is to be. So this means that which has been demonstrated. That which has been demonstrated. It just means I did it. I did it. I did it. That's all that means. You're supposed to put it, yeah, when you're done with the proof. Yeah, when you're proving something, only you put QED. If you don't want to put QED, you can just sign your name to it too, like a work of art. I'll be fine with that. Okay, but you should put something there to signify that you've completed the proof. And QED is usually what people put. Sometimes you might see. Sometimes there's just like a little box there. That's kind of another stylistic thing that I've seen in proofs. A little box just means that it's the end. It's a closure. You could sign off by saying more, please, if you want, like a quote from Oliver, like I love these things. Give me more proofs. You can do something like that. But you should sign off with it. All right, let's prove property 3. Property 3 is the natural log of x to the n equals n times the natural log of x. That's the B property. Okay, so step 1 for a proof, we draw a line down the middle, and then we pick a side that has more information. I think the left side has more information because it has a power of x. Okay, so I'm going to start on the left side. Now, here's what I'm going to do. I'm going to write the natural log of x to the n as the natural log of x times x times x dot 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 times x. And how many of those x's will I have? I will have n of those x's. Very good. And the reason there would just be rule of exponent, right? Or definition of an exponent. That's the definition of an exponent, isn't it? It tells you how many factors of the same type you have multiplied together. So I have n of them. All right. Now that I've used the definition of an exponent, I've turned them into products. So now I can use property number 1. So this becomes the natural log of x plus the natural log of x plus the natural log of x plus dot 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 plus the natural log of x. And how many of those do I have? N of them. And the reason would be property 1. Property 1. Well, now I can use the property, bless you, of multiplication. What can we do if we have the same term added to itself n times? Put what in front? The n. I could say that that's n times the natural log of x, right? Just like if you had 2 plus 2 plus 2 plus 2, there's 4 of them there, so that's 4 times 2. Yes, yes? That's the definition of multiplication. Okay, does the left side look like the right side? Yes, it does. So we're done. I'll put a little box instead of QED. Fantastico. Okay, so do these rules actually work? Yeah, they work. They work. So you need to memorize those 3 properties because they are basically the 3 properties that logs are famous for. They make molehills out of mountains. They divide and conquer. They break things down. All right. All right. After the warm up, I think we could do this. Expand this in one fell swoop. Ooh, that means in one step. No intermediate lines. We're going straight to the final fully expanded answer. Now, first of all, it's not natural log, is it? It's log base 7, which is okay. Those rules for logs work with all legal bases, between 0 and 1 for decay and greater than 1 for growth. So let's take inventory here. How many factors do we have? I got a 5, an x squared, a cube root of blob, a 2, a y, and a square root of blob. How many factors is that? 6. I have 6 factors, okay? Or 6 factor groups. That's going to translate to 6 terms. I'm going to have 6 terms, okay? 3 in the top and 3 in the bottom. Yes, yes? There's going to be 3 positive terms then that come from the top, and there's going to be 3 negative terms that come from the bottom. Now, in terms of exponents, where do I have exponents? They come out front. The squared is going to come out front. I have a cube. I have a cube root and a squared. That's an exponent, right? I can combine that into one exponent. And then I have the square root. That's another exponent, implied exponent. So I have 3 different factors that have exponents that are going to come out front. So here we go. Ready? Let's start in the top left. We get log base 7 of 5. There's the first factor. Plus, leave a little space, log base 7 of x squared. But where does the 2 go? Out front. There it is. So it's plus 2 log base 7 of x. Plus, we're still in the numerator. So it's going to be, leave a little space, log base 7 of 2y minus 1. Now, what would the combined exponent be when I get rid of the cube root and write it as a fractional exponent? It would be 2/3. Very good. There's already a squared there, so that's 2 in the numerator, and then times the third makes it 2/3. That 2/3 goes where? Out front. There you go. So that's expanding the top in one fell swoop. Now we'll go to the bottom. So now I have minus log base 7 of 2, minus log base 7 of y, and then lastly here, I get minus, leave a little space, log base 7 of x plus 1. And what would the exponent on that be? It would be a 1/2, which now goes where? In the front. 1/2 log base 7 of x plus 1. Nothing to it, right? We expanded it in one fell swoop, just like we did in the warm-up. That's the expectation. You should be able to do that.
Could you also put a parentheses around the bottom part and like make them all plus and just put a negative out front?
Yeah, but I want you to get rid of that parentheses. Okay, if those are plus signs in there, I want you then to distribute the negative so that you don't have the parentheses. It's considered more simplified when there's fewer grouping symbols. So we want to expand it all out. So that's why it wouldn't be illegal to do that, but then you'd have a whole other step. You'd have to go to a whole other line where you're doing nothing but distributing that negative. So what I want you to think about is that every factor in the bottom is always just going to be a negative sign. Okay, expanded out, it's going to be a negative sign. But what you said is not incorrect. It's just not fully expanded. We got to distribute. Okay, now, it's easy to expand in one fell swoop. It's not as easy to condense in one fell swoop. So when we condense, we usually condense in multiple fell swoops, right? More than one step. More than one step. Okay, so this one says to condense it and then simplify. So if you look at this expression right here again, first of all, it's not fully expanded. There are certain terms that have multiple factors in it, namely the last 2. But that's okay. I want to condense it, so I don't need it to be fully expanded in order to condense it. Now, if you remember, when we expanded, the last thing that we did as we were writing this stuff down was bring the exponents out front. The last thing that we did was bring the exponents out front. So when we're going in reverse, guess what the first thing we're going to do is? Take the exponents that are out front and take them back where? Not in the back, but we're going to put them up back as exponents. Yeah. Now, I have a 3, a 1/2, and a 2 in front. Don't worry about the negative in front of the 3. It's easier if you just make the term negative and just bring up the 3. So I'm going to bring the 3 up on the 2, the 1/2 up on the x, and the 2 up on the quantity 3x. And I'm going to take a whole line to do that. So I get negative natural log of 2 cubed, which is easier than positive natural log of 2 to the negative third, minus the natural log of x to the 1/2, plus the natural log of the quantity 3x squared, plus the last term doesn't have anything to bring up. So I do that first. Now that I have my coefficients of 1 or negative 1, that's what we want. The coefficients are 1 or negative 1. Now I can pull out a log. Pull out a single log. So for me, I'm going to have the natural log. Now, do we have any negative terms? Yeah. If you have at least one negative term, you're going to have at least one factor in the denominator. So you might as well build a shelf, your vinculum. Okay. Now, every argument that comes from the negative term gets multiplied in the bottom. And then every term's argument that's positive gets multiplied in the numerator. So in the bottom, I'm going to have a 2 cubed and an x to the 1/2, and they're multiplied in the bottom. And in the top, I'm going to have a 3x quantity squared and a 2y squared, like that. And then we simplify the argument. All right, so let's see what we could do here. 3x squared, what is 3x quantity squared also known as? 9x squared, very good, times the 2y squared. And then the bottom 2 cubed is known as 8. And then x to the 1/2, if I get rid of the 1/2 exponent, is the what? Square root of x. Yeah, so we'll put it in square root form. So that's the first step in simplifying the argument. I can go further now. That's the natural log of. Let's see what we could do here. This 2 and this 8 divide out to give you 1/4. Now, if you leave the x squared in the top and the square root of x in the bottom, you're not going to be able to combine them. Because there's an x in the top, I might want to leave this as x to the 1/2. Why would I want to do that? So that I can do what with the x's? Well, I can combine them, right? What does the rule say for exponents when you're dividing and the bases are the same? What do you do with the exponents? You subtract them, right? Subtract them. What's 2 minus 1/2? Yeah, two minus 1/2 is 1.5, which is 3/2. Yeah. So I'm going to have a 9 in the top, a 4 in the bottom. I'm going to have an x to the 3/2 in the top, and then a y squared, like that. All right, so what this is we have an irreducible number, 9/4. You can think of 9/4 as being its own number. And then we have one factor of x and one factor of y. So this would be as simplified as it can get. Or you could say it's the natural log of 9/4 x to the 3/2 y squared. Or you could say it's the natural log of 9/4 square root of x cubed y squared. Any one of those are the exact same thing. But in the end, in the argument, we have one number, 9/4, or two numbers that are irreducible, 9 in the top, 4 in the bottom, one factor of x, one factor of y. I guess there's one other version it could be. Or the natural log, if we leave it in fraction form, it can be like this, 9 square root of x cubed y squared. It could be like that too. All of those are equivalent to each other. So it's easy to expand in one fell swoop. Not as easy to condense in one fell swoop. So we want to do it in sequence. Bring the coefficients in front up to the exponent. Leave the negatives in place, because that just puts it as a factor in the denominator. Then condense your products from the numerator that are pluses. Condense your products from the denominator, which are minuses. And then you just do, then you're simplifying the argument using your rules of exponents. All right. Questions so far? All right, example 7. What else can we do with these properties of logs? Well, it says use the properties of logs to evaluate. So without a calculator, they're like, this is like a little game right here. Log base 4 of 2 plus log base 4 of 32. Hey, is that log base 4 of 34? I know what I'm doing. Give me my certificate of completion, teacher. I'm good. No, that you can't do that. That's not right. That's not right. So we'll put that off to the side as something that doesn't work. Now, can we actually evaluate this? 4 to what power is 2? We know how to think about log base 4 of 2. That's the same thing as saying 4 to what power is 2? What's the answer to that? 1/2, right? It's the square root of 4. It's the square root of 4 is 2. Yeah. Plus 4 to what power is 32? 4 to the third power is 64. 4 squared is 16, which is too small, right? 4 cubed is 64, which is too big. So log base 4 of 32 is 2 point something, right? Do you think that's how we're supposed to do this problem? 1/2 plus 2 point something is 2 point something, or maybe 3 point something. I don't know. That's not the way to do this problem. I can handle the first one. If the second log base 4 of 32 was a nice rational number, I would just be able to combine the two and be done. But I can't do that because of the second term. So there's got to be another way to do it. So we'll put this off to the side, shrink it down, and put this off to the side as another method that doesn't work. Hmm. Boo, 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 boo. Any ideas?
And then I'll
What do you mean expanded out?
make 32
A whole bunch of 1/2s. Like, what do you mean?
like 64 1/2. I don't
No, you're the one that said it. What do you mean? So do you help me out? Log base 4 of what instead of 32?
like a whole bunch of log base 2 that might add up to 32.
Such as you said log base 2s
2 to the power 6 or log base 4 is 2 to the power 5.
of 2 to the 5th. There you go. Is that what you mean? Write 32 is the power of 2? That might work. That might work. Everyone agree that 32 is 2 to the 5th? Okay. And then what would I do in the first one? Just kind of leave it the same, right? For now? Because now they're kind of at least looking similar. Okay, now I still can't add them together because they're not like terms. But what can I do with the 5? I can move it to the front. Yeah. So this becomes log base 4 of 2 plus 5 times log base 4 of 2. Do I now have like log terms? Yes. These are like terms. Watch. I have one of those plus 5 of those. And those happen to be the exact same thing. So what's one of those plus 5 of those? 6 of those. 6 log base 4 of 2s. 6 log base 4 of 2s. Now we can come back and say, what is log base 4 of 2? That's 1/2. Now we can evaluate it. Now that's 1/2. And then 6 times a half is 3. Sweet. So if your jersey number is 3, you can put this number on the back of your shirt instead. And let the announcers have a grand old time announcing your number. It's the same thing. Yeah. Thanks for getting us started on that, Andrew. That's exactly how I would have done it. Try to get like logs. Your like logs are going to be log base 4 of 2s. So if you can write 32 as a power of 2, property 3 allows you to get the exponent out in front as a constant multiple. Fantastic. Fantastic. All right. You kind of got the idea of what to do. You try B on your own now. Chew on it, and then swallow it. Don't spit it out. Don't spit it out. What? Come again?
Wait, what?
What?
Oh, wait.
Oh, hold on. Hey, if the properties of logs, the 3 properties of logs, turn products into sums, quotients into differences, and exponents into constant multiples, then if you're trying to use those 3 properties, it would be very helpful to have your argument written as a bunch of factors raised to a bunch of powers, right? Because then the logs can handle those. That's your strategy. Try to write your argument as a product of something with multiple powers, possibly. So what does that mean? When in doubt, try and get your argument into its prime factorization. Prime factorization. And you can use factor tree or upside down birthday cake. Now that you have 80 written as 2 to the 4th times 5, can we not expand that out in one fell swoop? I have two factors, so I'm going to have two terms. So it's going to be 4 log base 2 of 2. Yes, yes? Plus log base 2 of 5. I put it right there. Yeah. What? This, right? I put what? This goes to here and here. Well, I haven't written that one yet. Yeah, yeah. Minus, I'll do it in red. I haven't really done. I'll just bring that one down. Wait, what? I'm just working on the 80. What? What 5?
That 5 that was right there, you put that.
All right. So this is log base 2 of 2 to the 4th. Yes, yes. And the 4 can come out front. So I'm left with 4 log base 2 of 2 to the 1st. That's the first factor. It's multiplied, so it's plus. Yes, yes. And then it's log base 2 of 5. I expanded it in one fell swoop.
So log base 2 of 5.
Well, yeah, well, let's do the first term first since it's in front. The 4 goes along for the ride. What is log base 2 of 2? It's 1. Log base 2 of 2 is 1. So I get 4 times 1, which is just 4. Or you can look at it up above. Log base 2 of 2 to the 4th is 4. So I get 4. And then what happens with these two fellas? They subtract out to give you what? 0. What's 4 plus 0? What's the answer? 4. Oh, my gosh.
I got the same answer.
Oh, well, tell me how you did it, Maestro. Is there more than one way to skin a cat?
Yeah.
Absolutely. The goal is to get that skin off that cat. As long as at the end you have a skinless cat, it's mission accomplished. Meow. All right, let's look at the Brady way to do it. What'd you do, Brady?
I did log base 2, 80 over 5.
Oh my goodness gracious. You condensed it, didn't you? You condensed it. And what is 80 divided by 5? That's 16. Holy moly, smokers. And now, what did you do? Did you just rationalize what it is?
Yeah.
2 to what power is 16?
4.
2 to what power is 16? It's 4. Oh my gosh. You know what? I think that your skin came off your cat a little bit easier than my skin came off my cat. Yours was a lot more tender. It just fell right off the cat. Isn't Brady's way easier than mine?
Yeah.
That's kind of an opinion, right? I don't know if it's fewer steps or not, but it does seem easier. I condensed. I have log base 2 minus log base 2. So I can divide those arguments, which gives me 16. And now 2 to the 4th is 16, so the answer is 4. Which way is actually correct? They're both correct. And this is why students hate logs, because there's more than one way to skin a cat. U.S. students are trained to like do this when you see that, and to have just one clear path to the answer. You're just like, don't tell me that there's more than one way. Just tell me one way to do it so I can memorize how to do it, and then I'll just do it on the test, and then I can move on to the next class. But this class is about thinking, and there are more routes that can take you to the answer than just one, right? If you drove home from here to home this afternoon, there are many different roads that you could take to get you to your house, right? Some are more scenic than others, right? You might see skinless cats along the way, right? Or dead deer. There's a dead deer right in front of my house this morning, and I was like, did I drive in my sleep last night and pass out and hit a deer? So I gotta deal with that. I don't know what to do. Just let the buzzards get it, and then just get the bones, and then call animal control. I was thinking about just letting the buzzards get it, and then when it turned to bones, I could just like pour acrylic over it and make like a nice coffee table out of it or something. Like, are those deer bones on that table? Yep, sure are.
Was it a bug or no?
No, it was a little fawn. Yeah. So it'd be a little coffee table. But that's a lot of acrylic to pour on there. It's not cheap.
No.
Yeah, I may just call animal control, Cheyenne. That's a better idea. Maybe harvest the backstrap first.
Yes.
All right. Avoid these common errors. Avoid these common errors when working with logs. Now, everything in this box is an error, okay? They're not equal to each other. This is what students try to get away with every single year, and every single year students lose thousands upon thousands of points because they try this, and it doesn't work. Log base b of x plus y is not equal to log base b of x plus log base b of y, okay? You cannot distribute a log inside its own argument. It doesn't work that way, does it? Okay? If you have more than one term inside your argument like this, you're kind of stuck. There's really nothing you could do with the left side. You're stuck. In fact, if you have the right side, what is the right side actually equal to? Yeah, the right side is actually log base b of x times y. Those are actually equal to each other. It's not the left side. All right. Here's another one that doesn't work. The quantity log base b of x to the 8th power. You cannot bring the a out front and say it's a log base b of x. Why not? That's not how it works. Very good. That a is an exponent on the entire log, not just on the x that's the argument. Okay? That bring it out front rule, the b rule, only works when that power is on the argument. This right here is actually equal to log base b of x times log base b of x times dot 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 log base b of x a times. That's what that means. There's a of them multiplied together. This one is actually equal to log base b of x to the 8th power. If you want to put parentheses like that to emphasize it, there you go. Okay? So those are what they're equal to, but they're not equal to each other. Got it? All right. Oh, here's another one that students try to use. Log base b of x divided by log base b of y is equal to log base b of x divided by y. Sometimes they start with the right-hand side and turn it into the left-hand side, and sometimes vice versa. Okay? You're stuck. If you have something like the left-hand side, you're kind of stuck. There's really nothing you could do. The right-hand side, there is something you could do, though, right? This is actually equal to log base b of x minus log base b of y. But it's not equal to the quotient of the logs, right? The quotient of the logs is not equal to the logs of the quotient. And then finally, this one is one that we need to be very careful about. If you have log base b of ax to the n, why can you not bring the n in front?
Because it's not part of that term, like the whole thing.
It's not.
It's only on the x, it's not part of the whole term, right? This n is only on the x. If you bring it out front of the whole thing, you're assuming that it's the quantity ax to the n. Like up above, we had 3x to the whatever power. So you can't just see an exponent and say, it's got to come out front. You have to be able to isolate it. So what you could do here is say that this is log base b of a plus n times log base b of x. That's legal, right? Give the a its own term, and then you bring the n out only on the x. That's what that's equal to. The right side is equal to this. It's equal to log base b of the quantity ax to the nth power, which is different than just ax to the n. So those are equal to each other. Those are equal to those, but they're not equal to each other. Common mistakes, things to avoid doing. All right. What other kind of fun can we have with this? Well, let's take a look at example 8. The natural log of 2 is about 0.7. Has anyone here heard of the rule of 70 in your science class or biology class? The rule of 70? You remember what it said? It's doubling, right. The rule of 70 gives you an approximate number of years for something to double if you know the growth rate. Okay? And it comes from the fact that the natural log of 2 is about 0.7. The 2 is the doubling factor, and the 0.7 is 70 as a decimal instead of a percent. Okay? So if you ever have the rule of 70, it comes from the natural log of 2 is about 0.7. If the natural log of 2 is about 0.7, we can evaluate, or approximate, I should say, the natural log of 8. What should be my goal here? If the only tool I have is a hammer, I have to make everything that I want to use it on look like a nail. Agreed? Right? If the only tool you have is a hammer, you got to make everything you want to use it on look like a nail. So the only tool I have here is the natural log of 2. So I got to make everything that I'm working with look like the natural log of 2. That's what I mean. I have the natural log of 8.
That's 2 cubed.
But 8 is 2 cubed. There you go. There you go. So kind of what Andrew was recommending earlier. Let's write this as the natural log of 2 cubed. And now that it's 2 cubed, what can I do with the 3? Bring it out front. 3 natural log of 2. Now remember, when you work straight down, you don't need equal signs, right? The equality is implied. When you work straight down, you don't need equal signs. The equality is implied. But once you go to an approximation, you need to add squiggles. I am now going to substitute the natural log of 2 with what it's approximately equal to, 0.7, and then I can multiply and I get 2.1. And then I don't put the squiggles again. I only put the squiggles one time. Okay, 3 natural log of 2 is approximately 3 times 0.7, but 3 times 0.7 is actually equal to 2.1. Does that make sense? So we don't keep putting squiggles. We put the squiggles one time. Work straight down. All right, there you go. It's actually a little bit smaller than 2.1, but 2.1 is pretty darn close. All right, natural log of a fourth. I got to make that look like the natural log of 2 somehow. How can I write 1/4 as a power of 2? 2 to the negative second. You should be able to do that in your head. That's 1 over 2 squared. 4 is 2 squared. 1 over 2 squared. Bring it to the top, you get 2 to the negative 2. And now what can I do with the exponent of negative 2? Bring it out front. So I get negative 2 natural log of 2. And now I put squiggles, negative 2 times 0.7, and I get negative 1.4. It's an easy, right? All right, you do this one on your own. I'll do it up here quietly. Practice the proper notation as well. All right, you should get 3.5 because you can write square root of 2 is 2 to the 1/2. Bring the 1/2 out front, so you get 1/2 ln of 2. Squiggles, 1/2 0.7. Half of 0.7 is 3.5. I'm sorry, 0.35. 0.35. Yeah, that's me not running through the tape at the end of the race. Half of 70 cents is not $3.50. I would not be a good cashier.
I wish.
Yeah, it's 0.35. Yeah, we can use that kind of money in today's day and age. All right, log base 4 of 8. What the heck? Okay, so that's log base 4 of 2 cubed. 2 cubed gives me 8, and the square root makes it 3/2. Very good.
We divide it by 2.
Divided by 2? Why would I divide it by 2?
4 divided
I, let's bring 3/2 to the front. And that's what we did before. 3/2, log base 4 of 2. Now, here's the deal. I actually think I know what log base 4 of 2 is, right? I think I can actually evaluate that. 4 to what power is 2? 1/2. So I'm going to go to the left here and say that's 3/2 times 1/2, which is what? 3/4. So it's 0.75. But if I wanted to use the fact that the natural log of 2 is about 0.7, what could I do to change the base from log base 4 to log base e? No. If I wanted to change the base, the change of base formula. Yeah, let's try that. Let's see if we get something that's close to 3/4. This is just now a little activity here. This would be the natural log of 2 over the natural log of 4. The natural log of 2 over the natural log of 4, which is now the same as 3/2 natural log of 2 over the natural log of 2 squared. Which, if I bring that out front, becomes 3/2 times 1/2 times the natural log of 2 over the natural log of 2. I bring the 2 out front and the bottom, and it becomes a 1/2 factor. And what happens with the natural log of 2's?
A equal out to 1.
Yeah, I don't even have to say approximately 0.7 anymore, because whatever they are, they divide out with each other. They divide out to give you 1. So that gives you 1. And what's 3/2 times 1/2? 3/4. So either way, we don't have to use the squiggles here. Which method is correct or more correct? The green version or the green that turns into the blue? Both. They're both more correct. Which one's more efficient, of course? The green one. Yeah, because we know what log base 4 of 2 is. It's 1/2. But if we didn't, we could still use the properties of logs to proceed. And in this case, got an exact answer instead of an approximate. So there you go. Those make good multiple choice questions on tests. All right, I think we're going to stop there. We'll pick up with Ebbinghouse's law of forgetfulness tomorrow. You probably have talked about Ebbinghouse's law of forgetfulness in Mr. Kilford's psychology class, because I know he talks about it. All right, we're done for today. Good job, guys.